in section 1.8 continuity, and yeah, we're going to take it down a notch from section 1.7, so get excited. Continuity is, a lot of what you might think it is, things that are continuous. And then, of course, we just go into a slightly more technical calculus type definition. But the definition of continuity is, let's say we have a function and it's defined on some interval. And that interval contains the x value a. F of x is called continuous at that value if the limit as x approaches a of the function is f of a. So f of x is said to have, or otherwise, so if you don't have this, otherwise your function is said to have a discontinuity. Discontinuity at x equals a. So it's discontinuous. So either it's continuous or it's discontinuous at a value. So in order to be continuous at a, so it's like we're taking from this definition, what that tells us is that we have three conditions that need to be met. So we need to have f of a. There needs to be an actual value to be continuous. So f of a exists. And we need to have the limit as x approaches a of f of x. That also has to exist. And then, of course, the key thing is to see that the limit as x approaches a of f of x needs to equal f of a. So if any one of those things is not true, you do not have continuity at a point. You are not continuous. And so we're going to take a look. And like I said, this is really like what you think it is. If you put your pencil on a point and you never lift it up, you're going to have continuity on some interval. But once you have to do something weird and that pencil comes up, then you're going to have the issue of a discontinuity. So let's consider our function f. It's over here. This is f of x. And we're going to consider at these certain values, do we have, are we continuous or not? So take a look at a. So we're x equals -2. So take a look at x equals -2. And what I want you to do for each of these, A, B, C, and D, is I want you to think about, do all those conditions apply? Or are any of them do we not have any of them? Because if we don't have any of them, we don't have continuity. So when you look at x equals -2, I would ask you, just by looking at it, do you think this function is continuous or discontinuous at x equals -2? And what we would then do is show in this more formal way whether it is or not. So we can't just say yes or no. So let's check our conditions. So we want to know, does f of -2 exist? So we come over here. F of -2 exists. It is this value right here. F of -2 is 3. Then we're going to say, is the limit as x approaches -2 of f of x, does it exist? So when we think about the limit, it's like, okay, well, we're coming down here and we're coming down here, and we're getting infinitely close to a value, which is what it means to have a limit exist. And we see that we are approaching the y value of 1. So that's condition 1, condition 2. So now the question is, does the limit as x approaches -2 of this function equal f of -2? And what we see is, well, f of -2 is 3. This limit that we're talking about is 1. And so those are not the same value. So condition number 3 is not met. And so because of that, we are not continuous at x equals -2. So what would be a really good idea at this point would be to try to do the other 3. See if, kind of follow along to each condition, see if you have it or not, make your decision. You might have values that are not perfect, an estimate, it's no problem. Okay. Also, this is what's called a removable discontinuity. go. Because it's literally just like this hole. And so it's like basically the continuous part has just been removed. We have this other value that's up there, you know, this value of f of negative 2. It's just not what the limit is. So that's what's called the removable discontinuity. Okay, moving on to B. And I did put these all on the same page just so that we'd have our picture. But at x equals negative 1, let's take a look. So f of negative 1, let's see. So we look at f of negative 1, and we do have a value. It's not quite 1. It looks like I might have to just estimate here, 0.8. But it's there. Now when I think about the limit as x approaches negative 1 of the function, you might remember, oh, hey, I'm coming in from the right side. Yeah, and I, hit 0.8. But if you're coming in from the left side, what you should hopefully notice is you are not approaching the same value. So as you approach negative 1 from the two sides, you're actually approaching different y values. So because of that, we can already see that this limit does not exist. So because this limit does not exist, we are not continuous at x equals negative 1. Now this is what's called a jump discontinuity. And that is because, as you can see, you have to jump from one value to the next to get to either side of that limit. So it's called the jump discontinuity. It makes sense at a jump. Now at x equals 1, let's take a look. What is f of 1? So taking a look at where we have 1, hopefully you notice we've got an issue here. We've got a vertical asymptote, and there is no value at f of 1. This does not exist. This value does not exist. And so right there, because the value does not exist, well, you can't have a limit like that equals a value that does not exist anyway, no matter what. And so here we are. We can already say not continuous at x equals 1. And this is just called an infinite discontinuity. You might be able to see why, because we're approaching these infinite limits. And now let's take a look at x equals 2. You might have to be able to guess already what's going to happen here, but we'll take a look. So at x equals 2, let's take a look. f of 2 is 1. And the limit as x approaches 2 of this function, well, we're coming in on this side, we're coming in on this side. I guess I can do it this way. You guys are mirror image. So it's going like this, closer and closer on each side to 1. And so, of course, as we can see, f of 2 does in fact equal the limit as x approaches 2 of the function. They're both equal to 1. And so because of that, excuse me, we have 1, 2, 3 conditions satisfied. So we are continuous at x equals 2. There we are, a lot on the page. Okay. Now, we have a few things here. We have a couple definitions. So we're continuous. You can also be continuous from the right or from the left, as long as you have a value at wherever you're approaching, and you have that limit from that side that is also approaching the value from that side. And the same thing, so from the left or from the right. So again, the key thing to see here is you only have to be continuous coming in from that one side, because you're talking about specifically being continuous from the left or from the right, but you do need to have an actual value there. It can't be a whole or like an infinite. So taking a look at the graph that you have, f of x is continuous from the right at which integer values, and f of x is continuous from the left at which integer values. So what I'd like you to do is just take a minute, pause this, take a minute, and see which integer values, so those are integers, so like not decimals or fractions or anything, just which integer values, positive or negative whole numbers, and 0, are we continuous from the right or the left? And then come back and see if you're right. So the values in which we are continuous from the right is meaning if you come down from the right, you've got a limit, you've got a value at that limit, and we're just talking about the integer values here. So from the ones that we see on this actual graph, we get -1, 0, and 2. And that's because, I'll just have to talk it out. I have my notes here, but you can look at your notes right in front of you. So thinking about -1, so notice we come down and reach -1, and then there is a value at -1. At 0, that is an integer value. We're approaching a value, and then there's a value that exists, as well as at 2. So at 2, we come up and we are continuous from the right. From the left, the only value on this graph is just at 0 and 2, excuse me, 0 and 2. So notice that we don't have continuity at all at -2. We have continuity from the right at -1, but not from the left because of that hole up at the top. At 0, both sides, we don't have any continuity at 1. And then at 2, we also come in at both sides. So those are the values that we have. And a note here at the bottom of the page and the bottom of my slide is to note that something can only be continuous if it is continuous from the left and the right, because of course that means that a limit would have to exist. And if a limit does not exist, then you couldn't even have continuity, because like total continuity, because you don't have a limit from the left or the right. So you need to have both of those. Okay, so let's take a look now at just a rational function. So we have this rational function, and we're asked where it's continuous. So a lot of continuity, when you're looking at it like this, has to do with domain. Because if you have an issue with your domain, you're probably going to have an issue with continuity. So the big things to see here is you've got to ask yourself, what type of function is this? And this is a rational function. We've got a polynomial in the numerator and a polynomial in the denominator. What we know about rational functions is that we have a big issue when the denominator is 0. So we look and say, what would make the denominator 0? And that's going to be a value that's not in our domain. And that's what you want to understand about a rational function like this is every other value is fine. I can put in anything, but I can't put in -1 because then I'm going to divide by 0, and we can't divide by 0. There's an issue here with asymptotes. So f of x is undefined at x equals -1 because of that domain issue. And so we actually know just from that that that's the only thing that's going to give us a problem. So now we can say, thus, f of x is continuous everywhere except x equals -1. Now, there's a couple different ways you could write this. If you were to think about interval notation, we can go from -∞, put in any value all the way up to -1. -1 is a problem. And then we could go from the other side of -1 all the way out to infinity. And so, like I just said, this would be how you could show this in interval notation. Okay, now we have find a so that our function is continuous for all x. And we've seen a little bit of this when we talked about limits, but it was literally more about limits. And that's actually what comes back here anyway, so it's, makes sense. But, talking about continuity. So the way to do this would be to first think about those 3 conditions that we need. So the only place where we're going to have an issue, this is a line, this is a quadratic. Those are quadratics and lines are smooth and continuous. So the only place where there could be an issue with continuity would be at 1. So that's what we care about. So that's what we want to think about our conditions. So if we put in f of 1, we want to think about what is the value at f of 1. Now I want you to notice that x equals 1 in that top piece. So if we were to plug that in, we're going to get 3 times 1 plus a. Well, we get 3 plus a. Okay, so the big thing here is we got to figure out what a is so that, you know, this quadratic can meet up with this line and we have continuity. So we have 3 plus a. Now let's look at the limit on either side. So the limit as x approaches 1 from the left-hand side of this function just means, okay, so when we are approaching 1 from the left-hand side, so that's when it's less than, coming in, we still have that 3 times 1 plus a, or 3 plus a. And then when the limit as x approaches 1 from the other side of this function, so now we're coming in from the right side, the positive side, so when x is greater than 1, now we just plug that into our other function. See what we get? It looks like a -1. And of course, the big idea here is we want those two limits to exist. We need those two limits to exist. So that's going to tell us that we want 3 plus a to equal -1. So a is going to have to equal -4. And so as long as that happens, we are okay. So we have a equaling -4. And so that tells us that our function is going to be 3x minus 4 and x squared minus 2x on the following intervals that we were given. So x less than or equal to 1, x greater than 1. So if you were to graph those two pieces, you would notice that they are going to meet at the point, at 1. And then as you can see, it's going to be 1, it looks like 1, -1. And one of them is going to go like this, one's going to go like this, but you're going to have continuity. You could go and not have to lift up your pen if you were to draw. Okay. One more here, and then maybe we'll take a break. So for part 2. So we have a function, it's continuous. Oh, this is a definition. We have a function continuous on an interval if it is continuous at each number on that interval, right? So, you know, if you got a hole, you don't have it. If it's nice and smooth and continuous at each value, you're good. So just another example, where is f of x continuous? So we have another function. So big things to see here, of course, very, very similar to what we just did. We have a line and we have a rational function. So all we just do is recognize that this rational function has no issue. It actually doesn't, because there's no value that can make that 0 in the denominator. No matter what you plug in, you're going to square it. Well, that's positive. You're going to add 1. That's positive. So those two things actually have domains of all real numbers. So the only place you're going to have an issue is 0. So let's take a look at what happens at 0. So f of 0 is going to come from the piece that has the equal part. And if we plug it in, we get 3. Now, the other thing we have to think about is our limit. So of course, the limit as x approaches 0 from the right side of our function, that's what we just did. We already know that that's 3. Then if we look at the limit as x approaches 0 from the other side, that's that rational piece. Oops, other side. I don't need that little line there. Okay. Then what we see is, surprise, surprise, maybe, that when we come in from the other side of this function, if we plug in 0, we get 0 plus 3 over 0 plus 1. Well, hey, that's 3. So what we actually find is that f of 0, since each side is equal, we have a limit that exists and equals 3, plus it equals the function value. So we have all of our conditions met. Everything is good to go here. I'm just going to do that condition number 3. Everything is good. So even we didn't have to do anything and we are fine. So we can say thus f of x is continuous on, and then this is all real numbers. So that's just the fancy notation. One of my students called it the fancy R for all real numbers. And that's the continuity here. It's everything. Everything at all.